Okay. Welcome everyone to our first Monash Cybersecurity Seminar of 2021. So today we are welcoming Giulio Malavolta, who is a faculty member at Max Planck Institute for Security and Privacy, where he is the head of the Cryptographic Systems Group. His research work revolves around the theoretical and applied aspects of cryptography, and he is broadly interested in the intersection with other disciplines like computer security, concurrent systems, cryptocurrencies, game theory, and quantum computation. And today he will talk to us about obfuscation from circular security. So over to you. Thank you.
Okay. I'm now sharing my screen. I hope you can all see it. Good. So thanks a lot for having me. It's a great pleasure to speak and to start hopefully better year than the previous one. And yeah, so today I want to talk about indistinguishability obfuscation from circular security, and which is based on joint works with Zvika Brakersky, Nico Dotlink, and Sanjay Garg. And so before I start, I want to say that so there are a few things that I want to make clear. So the first thing is that if you have any questions at some point, you shouldn't wait until the end of the talk. You should just go ahead and interrupt me. If I don't see your question, then just unmute yourself and interrupt me. I'd be happy to answer any question during the talk. I think it's better if we make it an interactive experience. And the second thing that I want to mention is that this is a talk that doesn't assume any prior knowledge with the literature on obfuscation, which I know can be pretty intimidating. And we know we're going to go through all the steps together. Of course, we're going to just do a cursory look on these results, this line of work on obfuscation. And I'd be happy to point you to the papers in the end of the talk for more for those of you who are curious about the actual technical details. Okay, so what is this talk about? This talk is about a new candidate construction of indistinguishability obfuscation. And the sales pitch for this construction. So the main point that me and my co-authors want to stress is that this is a simple construction. So maybe the literature on obfuscation has kind of the history of being not so accessible, and we believe that this is a big departure from the state of the art. And essentially, anyone that spends a little bit of time reading our paper should be able to grasp the main idea of our construction without too much prior knowledge. So our results, the second important point is that they are only based on LWE-like techniques. So our final scheme will be based exclusively on the harness of problems over lattices. And this is an appealing technique because, at least in principle, we can conjecture that our scheme satisfies, it remains secure even in the presence of quantum computers. So the so-called post-quantum security. And in the end, we're going to reduce, well, besides LWE, we're going to reduce the security of our scheme against an assumption which is related to the circular security of encryption schemes, and I'm going to talk more about the assumption in the details. But well, for those of you who don't know what circular security is, essentially circular security says that the circular security for encryption says the scheme is semantically secure, even if you present the attacker with a key cycle, where a key cycle is just an encryption of a secret key under its own public key. Well, that's a one-to-one cycle, and a two cycle is essentially what is depicted here. So you encrypt SK1 under PK0 and SK0 under PK1. So this is just circular security for encryption. Of course, we'll have a more sophisticated version for obfuscation, but we'll see about this later. So for now, just think of circular security. Okay, so well, what is indistinguishability obfuscation? And indistinguishability obfuscation is the following task. So given program P, we want to take its code and produce a version of it which is unintelligible but still functional. So that means that the so-called obfuscated code, if I evaluate it on any input x, it will give me the same result of the unobfuscated code. So it will be P of x. Right. So and again, please note that so the difficulty or the power of this primitive comes from the fact that this is an non-interactive primitive. So I'm taking a program and obfuscating it, giving it away for the world, and everybody can query it on any input it wants. So what's the security that we are going to aim for? We're going to say that if we're going to require that if two programs P0 and P1 are functionally equivalent, that means they are identical on their output is identical on all input, then their obfuscations are computationally indistinguishable. And while this seems to be a very weak guarantees at first, we know in some sense that this is the best possible notion of obfuscation that we can achieve, modulo some factors in some polynomial factor in the security parameter. In fact, this thing turned out to be a very powerful tool. And we know by now that many very exciting primitives that we don't know how to construct otherwise, they are possible to be constructed using indistinguishability obfuscation, such as functional encryption, deniable encryption, non-interactive key exchanges, and multilinear maps. So essentially, obfuscation is sort of this bridge that connects us to this very powerful world where we have like all these fancy new primitives, and so it's a very interesting object, and together with one-way functions, it seems to subsume a lot of crypto as we know it. So this is something that I'm personally very interested in, and then I think it's an object that is worth studying. Oops. Good. So what I want to make like one slide for explaining a brief history of the constructions of IO, and tell where our framework position itself inside of this landscape. So historically the first line of work that started constructing IO, it originated with the work of Garg et al. In 2013, and they constructed IO from a very strong cryptographic object which is called multilinear maps. And since then there's been a lot of work directed into constructing and cryptanalyzing those multilinear map constructions. So on the positive side, these objects have received a lot of attention from the community. There has been a lot of cryptanalysis. On the less positive side, like many of these candidates have actually been broken for multilinear maps. Not all of them, but many of them. But for all of them, we really lack something that in cryptography, at least in theoretical cryptography, we like to have, which is like a reduction to a standard assumption, to something that we understand well. We think we have fair confidence that it's secure. So this has left theoreticians and cryptographers wary in general and very unsatisfied. So thereby there have been a bunch of parallel line of work that branched out to get to improve the state of the art. And perhaps one of the most prominent is starting from functional encryption and culminating with the recent work of Jane, Lin, and Sahai that constructed indistinguishability obfuscation from well-understood assumptions. And in particular, there are these 4 assumptions. So there has been a workshop recently where this construction, along with ours, has been explained very, very carefully. But just to summarize, these 4 assumptions are the LPN. So this is like a slightly new variant of LPN, but we are confident that it's a good variant of LPN. The learning with error assumption, LWE, the SXDH assumption of linear maps, and the existence of a pseudorandom generator in NC0. So this is a great set of assumptions. It's basically all the assumptions that we know that gives us public key encryption. Not exactly, but almost. The slightly unsatisfactory aspect is that this construction relies quite crucially on the uses of bilinear pairings and in particular on the hardness of the SXDH problem. And we know that the current instantiation of bilinear pairings are all broken by a quantum computer by Shor's algorithm. So this construction, so this line of work definitely doesn't result into a construction that can even plausibly guarantee post-quantum security with an actual attack given a quantum computer. Okay, and there are some other approaches that have been developed over the years to constructing distinguishability obfuscation. Maybe less popular than the above one, so the literature is less rich, but still it's worth mentioning because they are somewhat interesting. So, for example, there have been a line of work trying to construct indistinguishability obfuscation based on tensor products, or so on some new object called affine determinant programs. And finally, I want to mention, well, I should mention that there's been this work that which originated our line of work that's constructed indistinguishability obfuscation from the interplay of homomorphic encryption schemes. And this is going to be the focus of this talk. And again, as I said, this is what originated our line of work. And here was the original template to construct IO. So starting from a fully homomorphic encryption scheme, together with the Damgard-Urich encryption scheme, which is a linearly homomorphic encryption scheme which satisfies some special property that we needed, plus a random oracle, we showed how to construct an object that we call split FHE, split fully homomorphic encryption scheme, which in turn quite easily give us a version of obfuscation that is called exponential obfuscation, so XIO. And this is known to imply IO together with LWE via simple, well, not simple in retrospect, but by a relatively simple generic transformation. And I'm going to go over these steps more slowly, but I just wanted to mention the outline of this line of research. And again, so this was relatively a new approach, and again it had the advantage to be conceptually simple. However, in that paper we didn't provide any security proof against a simple and well understood assumption. So basically the assumption of the scheme was that the scheme was secure. We had some sort of argument in some artificial oracle model, but there was essentially no formal argument for security. And in particular, so another aspect is that this scheme was post-quantum broken. So again, we have an explicit attack using Shor's algorithm because of the Damgard-Urich encryption scheme, which is based on the hardness of factoring. So if we can factor large integers, then we can break down Damgard-Urich encryption. So again, this left us in a slightly unsatisfactory aspect. And very recently, last summer, 3 results, including ours, came out that essentially allowed us to bypass the usage of the Damgard-Urich encryption and constructed some variant of split fully homomorphic encryption from LWE-like techniques, so LWE by an interplay of LWE-based crypto systems. And for those of you who are familiar with this work, I want to mention that they all share many ideas, and we've been talking a lot among each other. We sort of have the feeling that the security of these schemes essentially draw all from the same common root, but they're all in a sense different. So there is our work together with the work of Gay and Pass that adopts a more like proxy encryption. So it somehow intrinsically relies on the fact on the ability to switch from one encryption scheme to another and leverage the properties of both. Whereas the construction of We and Wix adopts a more direct approach and just construct something that they call functional encoding, which is essentially a more general version of split FHE. they give a direct construction of that and show like an algebraic assumption under which this construction is secure. Okay. And again, the security of the scheme can be proven under a simple but new assumption. And as I mentioned before, the flavor of this assumption is that of circular security. So essentially, we want that things stay secure even though we publish key cycles and we give key cycles to the attackers. But on the positive side, the constructions can be conjectured to be post-quantum secure. Of course, we don't have nice results such as for LWE, so we don't have like nice worst case to average case reductions. So that's of course something that is missing. But we believe that this is a step forward, and of course the field is wide open. So if you're curious, there's plenty of room for improvement, and yeah, be happy to discuss if anybody has any ideas. Okay, so I think I'm going to start talking a little bit more about technicalities. So if someone has questions, I think now it's a good moment to ask. Okay, I don't see anything and I don't hear anything, so I keep going. Please interrupt me even later if some question pops to your mind. Good. So I want to define now a little bit more precisely what is exponential I/O and why we are even interested in that. So exponential I/O is nothing more than obfuscation for circuits. So it's just plain obfuscation. But we restrict ourselves in considering circuits that have a polynomial domain. So that means that, in particular, this means that I can, in polynomial time, evaluate a circuit over all possible inputs. So in other words, the size of the truth table of the circuits is polynomial. So these are very small circuits, and at first sight, not really powerful. And what are the conditions that we impose? Of course, we want that this obfuscation is indistinguishable in the same sense as we discussed before. So for any two functionally equivalent program, we want computational indistinguishability of their obfuscations. But in addition, we want something which we call non-triviality, which essentially says that the size of the obfuscated circuit is sublinear, and sublinear in a pretty strong sense, in the size of the truth table of the circuit. And note that the size of the truth table of the circuit is exactly n. As otherwise, if we didn't have this requirement, just writing down the truth table of a circuit would be a good obfuscation of a circuit. So that's not what we want, of course, that there's nothing happening there. But so the important requirement is that the size of the obfuscated circuit is going to be smaller than the size of the truth table of the circuit. So why do we even consider that? Well, it's not hard to see that it is very useful to consider easier classes of circuit whenever we are constructing obfuscation. So this is going to make our life much easier. And why is it fine to consider only this class of circuits? Well, there is a very nice theorem that says that if exponential I/O exists, in addition to the learning with error problems, then we can construct full-fledged I/O. So in particular, this says that if you are fine with the learning with errors assumptions, then you can, without loss of generality, focus on constructing XIO, right, and you get the full I/O. So that's great for us. We only want to consider obfuscation for this very small class of circuits. Okay. Well, here, of course, I'm being a little informal. In reality, there is like some sub-exponential loss of security somewhere, but maybe I'll refer you to the paper for a precise theorem statement. Good. So, and for us, what is going to be useful is that the theorem above is true even with pre-processing. So what does this mean? This means that even if I give the obfuscator access to a CRS, so through a uniformly random string, then the same still implies obfuscation. So let me be slightly more precise here. So now I'm giving the XIO access, random access to a common random string. And the size of this common random string can be as large as I want, even proportional to the truth table of the circuit N. Okay. Okay. So, and again, this is without loss of generality, because it turns out that this object implies full-fledged I/O. So I can take this object, construct I/O without a CRS, even if my CRS was apparently as long as the truth table of the circuit. And here I want to give you an intuition on why this is the case. And actually the intuition is relatively simple. So here on the left, you can see, this is my way of slicing the truth table of the circuit C in equally sized blocks. And it's not really important how big these blocks are, but you can really think of just each block to be of a square root size. And now it's not hard to see that even if my CRS is as large as the truth table of the circuit, if I can reuse the CRS across several instances, which is the case since the CRS is uniformly random, then the security of my XIO follows from a simple hybrid argument. So I start switching the first, and I can do it by, let's say, programming the CRS from the circuit C to the circuit C prime, and then I can go all the way and have square root n many hybrids, and then eventually I switched all the circuits. So this essentially says that constructing XIO can be done without loss of generality in the common random string model, even though this common random string can be as large as the truth table of the circuit. And the key word here is that we take the CRS and we amortize over different instances. Is there any question on this step? So this is just saying we're going to consider something with a CRS, and this is going to be without loss of generality. Good. So now from here on, our task will be to construct exponential IO, XIO. So I hope I convinced you that that's all we need in order to construct IO, and that's in fact the hard part of constructing IO. So that's the difficult part. And even all this, even these works that are like somewhat parallel, for example, the JLS work, they all go through a similar route. It's not exactly the same route, but essentially at the very core of their scheme, which is the same as happening in ours, there is a mechanism to securely take some weak class of circuit, compress its representation in such a way that the security of the evaluation is not compromised. So at the very heart of our construction, of their construction, essentially of all constructions of IO, there is a mechanism to compress the truth table of a circuit in something which is sublinearly smaller than the truth table. Okay, this is what is common to all this framework, and we know that XIO and this other tool allows us to generically crank up this compression all the way up to constructing full-fledged IO. All right. So how do we construct XIO? Well, our main tool is going to be what I call split FHE. And if you have heard the term functional encodings from the work of Wee and Wicks, you should think of functional encoding as somewhat a more general version of a split FHE with less structure. But for the purpose of this talk, you can forget about functional encoding and just really focus on split FHE. So what is split FHE? So first of all, I'm going to mention the split FHE is again a primitive that I can consider without loss of generality in the CRS model for the same reason as before. And this is essentially a standard fully homomorphic encryption scheme. So for those of you who don't know what a fully homomorphic encryption scheme is, I'm telling you in a very informal way now. So given an FHE encryption of a certain message M, there exists a publicly evaluatable algorithm eval that takes as input a ciphertext and a certain function f, and allows me to compute the encryption, so an FHE encryption of f of m, which is the result of the function applied to the message. And we said that the scheme is fully homomorphic if the class of is the family of functions that can be supported in the evaluation of the circuit is the family of all polynomial size circuits. So this is just a standard FHE. So where does the name split come from? Well, it comes from this additional algorithm that we are going to impose the existence of that takes as input a given ciphertext, any ciphertext. In particular, now we're just taking this ciphertext and creating f of n, and it computes a small hint, so a decryption hint that together with the ciphertext allows me to recover f of n. So, okay, now you're probably not really impressed. I mean, what is that even non-trivial? Why does this help? Okay, so first of all, before discussing this, I want to impose some condition about this hint to make this problem slightly more useful. So the first condition that I want to impose is that the hint is ciphertext specific. So this means that the hint, together with the given ciphertext that I computed the hint from, allows me to recover the content of that ciphertext. So in particular, in this case, it would be f of n, but nothing more than that. So because otherwise I could just publish the secret key of the scheme. So that's not an interesting operation. Of course, I can always publish a secret key of the scheme. That's not going to be helpful, but that would allow me to break all the ciphertext. In this case, I want to compute a hint that allows me to break a single ciphertext. Okay, so this is as far as security goes. But again, I need to impose another condition on the hint, which is that of succinctness. And succinctness means that the size of the hint should be sublinear in the size of the revealed message, as otherwise I could just decrypt my ciphertext and set the hint to be the plain text of that ciphertext. So the hint should be some sort of compressed information that allows me to take an FHE ciphertext and recover its content in a public way. Of course, computing the hint requires the secret key, but once I have the hint together with the ciphertext, anybody can recover the underlying plain text. Okay, and well, if you paid attention so far, I've been talking a lot about how obfuscation is about compressing things, so it shouldn't come as a surprise that that this requirement is indeed the crucial requirement for split FHE. Okay. So any questions up to now?
I have a question. Yes.
Please.
Do I want the split FHE to enable me to generate hint for any messages, or is it sufficient if I can just generate it for some set of messages?
Well, so in general, you need it to be you need to be capable of generating hint for any ciphertext. So yeah, so in general, I mean, you can be slightly more specific than that, but yeah, I'm not sure a meaningful what a meaningful relaxation would be. So in our definition, you can take any ciphertext and compute a hint. I mean, it would be okay to just be able to compute a hint for, like, I don't know, for like a predefined set of ciphertext, as long as the set of ciphertext is diverse enough. But I wouldn't be sure how to make it, yeah, to make a non-trivial relaxation. So let's say for the moment that any cipher, you should be able to compute a hint for any ciphertext.
Okay. Okay. Thanks.
All right. So it turns out that this is actually sufficient to construct like that. As I said before, like this compression feature that we were after is given by the hint. So I'm going to show you our split FHE actually implies XIO. And again, if you remember, XIO was sufficient together with LWE to construct IO. So once I show you this, then I'm done. I mean, of course, I still need to construct split FHE, but for the moment, let's just assume that split FHE exists, and let's see how to get XIO from it. So here's how the obfuscation algorithm work. So the first thing that I do is I take my circuit C that I want to obfuscate, and I compute an FHE encryption of the circuit C. Then I take the evaluation algorithm and perform the evaluation of the circuit C over all possible inputs 1 to n. And here it is important to keep in mind that the circuit that I'm obfuscating has a small domain. In particular, this means that n is a polynomial size number, so I can, in polynomial time, go through the truth table of the circuit. And what I will obtain after doing this operation is just an FHE encryption of C1 concatenated with all the values up to Cn, which is nothing but the truth table of the circuit C. Okay, so this is just an FHE encryption of the truth table of the circuit C. And then after that, I'm going to compute my hint, given the secret key, of the resulting ciphertext. And I'm going to set the obfuscation of the circuit C to be the FHE encryption of C, together with the hint that I computed through this operation. So this is going to be my obfuscation. And before telling you how I'm going to evaluate this circuit, first let's check that this is indeed a good obfuscation. So let's check indeed that the size of the obfuscated circuit is small enough. So the first component of the obfuscated circuit is just an FHE encryption of the circuit C, which is polynomial in the description of C, but potentially has nothing to do with the size of the truth table of C. If the circuit admits a succinct representation, which is the case that we're interested in. And the size of the hint, by the succinctness requirement that I imposed before, is much smaller than the size of the truth table of the circuit. All right. Good. So this is compressing. Fantastic. Let's see how to evaluate it. Well, to evaluate it, I can simply repeat the step above. So take the encryption of C, evaluate it over all possible inputs, and obtain an encryption of the truth table of C. And note that the FHE evaluation is a deterministic algorithm. I can always fix the randomness of this algorithm. So I will obtain exactly the same ciphertext. And now, together with the hint that comes with the obfuscation of the circuit, I can always recover the truth table of the circuit and then just read the output that I'm interested in, right? So that's exactly, essentially what's happening. I slightly oversimplified things in the sense that yes, the hint is small, but the public key of the encryption scheme might be large. It might be in particular proportional to the size of the allowed plaintext, which in our case would be the truth table of the circuit. So this is something I didn't put there. I simplified things a little bit, but in practice, you would have to put the public key of the scheme in order to compute the evaluation procedure. So that would be too large. But fortunately, as we learned already, when something is too large, we can always amortize its size away. As long as this thing is reusable, we can always amortize this size away by just repeating this operation, let's say square root many times, and dividing the truth table of the circuit in square roots size chunks. Right, so this is essentially the same transformation as before, as we already saw, but the purpose here is to just reuse the same public key across different instances of the obfuscated circuit. And this time, in order to evaluate, I will first look up the chunk that I'm interested in, recompute the resulting ciphertext, and use the corresponding hint in order to essentially decrypt the FHE encryption of that chunk. And then I'll look up the output that I'm interested in. Good. So I hope I convinced you at this point in time that split FHE is sufficient to construct XIO, and consequently is sufficient to construct fully fledged IO. So what is left to be done, well, what is left to be discussed, which is basically the technical core of our work, is how to construct split FHE. And again, here's another good moment to pause and ponder. If we have questions, I'd be happy to go over some parts if you were unclear. As otherwise, I will proceed next by explaining how to construct split FHE. I hear some noises. I don't know if someone is unmuted himself to ask a question.
Yeah, maybe I can ask again a question here. So
Go on.
do we have like many hints here, or is it just one?
Right. That's correct. You have one hint per block, essentially.
So in the original one, without this kind of like this square root on n by square root on n blocks.
Oh, so in the original one, you just have one hint, right, for the whole truth table of the circuit. But again, that doesn't take into account for the size of the public key. Whenever you want to really amortize for the size of the public key, you have to repeat the same procedure, let's say square root many times, with the same public key in such a way that the public key doesn't blow up the size of your obfuscated circuit. And then for each sub block, you will repeat the procedure as I described it before, namely take that block. Sorry, take the description of the encryption of the circuit, evaluate the truth table on that specific block, so end up with an encryption of that block, and then compute the hint specific for the encryption of that block. So you will do it square root many times. So you have to be a little careful with the parameters, but well, if you trust me on that, it can be made sublinear.
Mm-hmm. I see. Okay.
So again, here the code word is amortization. So we have something which is too long, like the public key would be very long. So it wouldn't allow us to achieve compactness or succinctness. And the way we deal with that is by just reusing it across different executions. So we amortize away the size of the public key. So this is a trick that we can always use as long as the information that we want to amortize for is reusable. There's going to be some informations which are not reusable, so we cannot amortize it away. And those, for example, hints are not reusable, right? So you really have to achieve compression of the size of the hint. You cannot amortize it away.
Yeah. Okay. Thanks.
Okay, I hope it makes sense. And now I want to spend the last 15-20 minutes of my talk explaining on a high level how to build split FHE. And here is going to be really just a high level idea on how a high level framework on how to build split FHE. And I refer you to the paper. I can give you the references in the end. I refer you to the papers for more details, and I'd be happy to answer questions if you're curious. So we're going to go gradually, and we're going to start with some simple but flawed attempt in order to construct split FHE. So the first component that we're going to use is just a standard fully homomorphic encryption scheme with something which is called almost linear decryption. So what does it mean, almost linear decryption? It means that to decrypt an FHE ciphertext, all I need to do is compute a linear function and then round up to the closest multiple of some q over 2. So essentially, you should think of it as just a linear function and then some rounding operation. Okay, so this is very common for FHE schemes to satisfy this structure, and I think most of the schemes that we know do satisfy this property. On the right side of the slides, we have the other component that we're going to use, which is going to be a public key encryption that satisfies two properties. So the first property is linear homomorphism. So this is just going to be a linearly homomorphic encryption scheme. And the second property is that it is going to have the structural requirement of having small decryption hints. And I'm not going to talk about how to actually instantiate this public key encryption scheme in this talk, but I can just mention that in the first version of our work that was published at Eurocrypt last year, we instantiated it with Damgard-Yurik encryption scheme, and you can show that indeed this scheme does satisfy the notion of split decryption. Whereas in our new work that came out last summer, we had to work a little bit harder to get this from a packed version of dual regel. And we will not get exactly this. We're going to get something similar to this, and then we'll have to work our way to construct fully fledged split FHE. But so for the moment, for the purpose of this talk, you can really think of it as a public key encryption scheme, which has small hints and satisfies a weak form of homomorphism. So the template is very simple. The idea is just to take an encryption and a fully homomorphic encryption scheme of our circuit C. And again, here there is nothing special about the circuit C. You just think of it as any message M, right? So now I'm just talking about split FHE, right? So I don't care about circuits or anything like this. Just this. I want to just talk about this building block split FHE. So I'm going to take an FHE encryption of my circuit C, compute the function that I'm interested in. It could be obtain the truth table of the circuit, like before, and then perform a key switching operation. So what does it mean, key switching? This means that I'm going to use the secret key encryption of the FHE, compute the linear part of the decryption of the FHE, and obtain essentially a public key encryption of a noisy version of the content of my FHE scheme, right? So why noisy version? Where does this noise come from? Well, recall that the decryption algorithm was a linear operation followed by the rounding, and we're not doing the rounding before. So the extra information, we just parse it as noise, okay? So here we have our public key encryption of a noisy version of the encoded truth table. And well, since our public key encryption scheme had small hints, we can just, well, return the hint of this public key encryption scheme. And this allows us to recover an encoded version of the plaintext that we were interested in. In our case, it will be the truth table of the circuit, plus this rounding noise that we didn't actually round because we computed only the linear component of the decryption algorithm. So this is structurally fine. So we could, in a perfect world, we could just do this and call it a day. Unfortunately, this is a completely insecure scheme, and in particular, the noise term cannot be disclosed because this is a problem for security. It's actually not difficult to attack this scheme. You should just think that well, if I reveal enough of those, and I'll get a system of linear equation in the secret key, and well, having enough of those, I can always recover a secret key by a Gaussian elimination. So this is not a good solution, but it points us towards the right direction, I think. And so I'm now going to turn the tables a little bit and flip things around. I'm going to give you a solution that is actually working, but for which we don't have a candidate instantiation. And finally, we'll work our way through something that is working and we can actually instantiate. Good. So now I'm going to assume that the CRS, so the common reference string, consists of instead of being uniformly random, instead of being just a bunch of uniformly random bits, is going to consist of public key encryption scheme of a bunch of ciphertext of some components S, where the component S is something which is small and random. I'm just going to parse this, the common reference string is just a bunch of ciphertext of small and random plain text. Okay, so let's assume for the moment that I have this object, that I can actually instantiate this object. Let's revisit our construction paradigm for split FHE. Okay, So the first thing that I'm going to do, as before, is I'm going to have an FHE encryption of the circuit C. And then, as before, evaluate the function that I'm interested in. In this case, it will be the computation of the truth table of C. Then key switch to my public key encryption scheme using, again, the linear homomorphism plus the fact that the FHE encryption scheme had a linear, almost linear decryption, so linear and rounding. And again, as before, obtain a public key encryption of a noisy version of the truth table of C. And again, here the Q over 2 factor is just to, you should think of it as just an encoding of the truth table of C that allows me to tolerate a certain amount of noise. So far is exactly as before. The only thing that I'm changing now is that I'm adding a certain public key encryption of S coming from the CRS to the resulting ciphertext before giving away the hint. Okay, so what I'm going to obtain is something that looks like a public key encryption of a noisy version of the truth table of the C plus this term S that comes from the encryption in the CRS. Okay, so if I have that, it's actually pretty easy to show that the resulting ciphertext is statistically close to a public key encryption scheme, to a public key encryption of an encoded version of a truth table of the circuit plus some term which is uniformly random, so it's statistically close to uniform. So for those of you who are familiar with the literature, what is happening here is that this term S is smudging or drowning away the noise resulting from the absence. And now that I have this, the hint can be safely disclosed because this uniform term U that results from the addition of noise plus S does not carry any information in statistical sense from the secret key of the FHE encryption. So, well, this is good. So this is indeed cautious. We can do this, and again, we can just as before, disclose the hint for the public key encryption, and allow everybody to recover the plain text. And as I said, this is a uniform term, so there is no leakage there. Again, in a statistical sense. And if you think about the attack of before, this would be the equivalent. So before we were giving a lot of linear equation in the secret key. In this case, we are giving a lot of noisy linear equation of their secret key, which is basically an LW sample, if you want to think about it that way. Good. So now that's fine. Well, unfortunately, the problem is that now the public key encryption scheme, the public key encryption of S is not a uniform string. So this is a correctness problem. So if you recall, the purpose of having a CRS was to take it and reuse it across different instances. And if we have something which is structured, so it has a particular structure, such as, for example, the encryption of something small, then we can no longer use it across different public key, because let's say under a certain public key, this will be an encryption of something small. But if I sample a uniform and independent public key and take the same ciphertext, in the best case will be another ciphertext, but certainly not an encryption of small with any noticeable probability. It might even not be a well-defined ciphertext, right? So this doesn't work. And this in particular means that we cannot reuse the CRS across different instances, and therefore we don't achieve any notion of compression. So yeah, that's not good. So we need to get around this problem. But you'll see that we're going to try to recover the same decryption mechanism, so the same drowning mechanism for the noise, But of course, we'll have to work with something which is a little less cooperative than this. So we're not going to assume that the common random string assumes consists of encryption of something small, but we really are going to assume that the CRS is just a uniform random string. And here is our actual solution. So if you didn't pay attention now, then it's the moment to tune in for our actual scheme work. So first of all, I'm going to assume an additional property of our public key encryption scheme is that it has something which is called dense ciphertext, which essentially means that if I take uniformly a random string, it will be with all but negligible probability a well-formed ciphertext. Now note that I can no longer assume that the underlying plaintext S is small, but instead it will be just a uniformly random value in the plaintext space. So I'm going to work with something which is still well-formed, so it will have some structure, but not as nice as I would like it to. Okay. Good. So what can I do with this? So first of all, observe that if I try to do the same strategy as before, right, it will fail miserably because this value S is full range, and it will, in particular, will act as a one-time pad to my. It will not only drown the noise, it will also drown the message. So it will be a mess. So I cannot use it as it is. Instead, I'll have to work a little bit harder. So now I'm going to assume not only that I'm given an encryption under the public key encryption scheme of the secret key of the FHE scheme, but I'm going to assume a two-key cycle. So I'm going to assume that I'm given an FHE encryption of the secret key of the public key encryption scheme. So why is that useful? Well, the first thing that I'm going to do, I'm going to evaluate the circuit pi homomorphically over the fully homomorphic encryption scheme. So what does the circuit pi do? So the circuit pi takes as input the circuit C, the encryption of the circuit C, together with the ciphertext in the CRS and the secret key encryption and the secret key of the public key encryption scheme. And I'm going to compute, as before, the truth table of C, together with this term Z. What is Z? Well, Z is nothing but the high order bits of S. So just take the ciphertext, which is a public key encryption ciphertext, peel off the layer of encryption, so decrypt it, and parse it as a bit string, and take the low order bits, so basically all the bits except for the most significant one, and throw them away. And I'm just left with the higher order bits, Z, as I define it here. And I'm going to take the negation of this. So I'm being a little bit informal. This is not exactly what you have to do. You have to be a little bit careful with how many bits you keep, how many bits you throw away. But for the intuition, let's just imagine that I'm taking, just a bunch of high order bits. And now I can proceed exactly as before. So namely key switch into the public key encryption. Add the homomorphically the encryption that I found in the CRS, so namely an encryption of S. And note what's happening here. Again, I'm adding the value S homomorphically. So so yes, S is going to add to be added homomorphically to the plaintext here, but the catch is that essentially the high order bits of S will not go and mask the plaintext that we're interested in, because we preemptively subtract them from the operation. So the fact that we computed minus Z here essentially allows us to say that this information, that's the one that we're interested in, is not affected by by adding this random string s. And now, again, informally speaking, you should think of s minus z as just the lower order bits of s. So essentially all the s except for the part that would cause problems. And again, this acts as a smudging term for my noise. And again, I obtain something uniform here, right? So again, by a statistical argument. Good. So, well, now I can take this encryption, safely release the hint, and I'm done. Right. So again, the property of my hint is that of succinctness. So, you know, it seems like I'm done. Well, not exactly. I mean, so this is actually our scheme, but we cannot prove it secure under the assumption that you would expect. And the reason why we cannot prove it is not as clean to prove security for the scheme is the following reason. So ideally, we would like to say that the noise is smudged by the lower order bits of s. But in order for this argument to go through, you need to make sure that these two terms are sampled independently. And this is not the case here. And specifically, the decryption noise might depend in some intricate way on the lower order bits of s, because it could depend on, so the information is there during the homomorphic evaluation. So we'll have to work a little harder in order to prove this scheme under a reasonable assumption, but it can be done. I won't have time to go through the exact assumption, but this is something which we call shield, which is called SRL security. It stands for shielded randomness leakage security. And I have some material to talk about that, but I think I'm out of time. So if there are no questions, well, I think I'm just going to thank everybody for their attention and conclude my talk here. Maybe if someone is interested, I can spend a little bit of time talking about the exact assumption that we prove things against.
Thank you very much. I think we can ask the audience if anyone has any questions. I have some questions, but let's first see if the audience has anyone, any questions?
I have a question.
Yeah, go ahead, Ron.
So where do you use, so you use the FH encryption of the SK PKE when you do the homomorphic decryption of S, right, to get the Z?
Yes.
But where do you use the other one, the PKE encrypt of SK FHE?
Oh, yeah, excellent question. So we use that in the key switch operation. So whenever we want to go from an FHE encryption to a public key encryption, the way we do it is by just evaluating again the decryption algorithm homomorphically. And to be a little bit more precise, we will not evaluate the exact decryption algorithm, just the linear part of the decryption algorithm, so just the linear function. But of course, in order to do that, we'll need to have the SK of the FHE encrypted under the PKE. So yeah, this is the place where we go.
Okay, yeah. All right, thank you.
Any other questions, anyone? No questions. Yeah, I was actually wondering about this. So you mentioned about this packed dual reggae. Is it like CRT packing?
No, it's not CRT packing. So we don't make any assumptions on the modulus. I mean, I think in the paper we require it's even, but that was just to make the analysis simpler. So you don't need to have, you know, the modulus to be a composite number. what we do is essentially packing means you have a version of dual regger which is slotted. So that means that a ciphertext will contain several slots, and you can put different plaintext on each slot. What's the advantage of doing that? Well, the advantage is that we can use a random string, which is much smaller than the actual plaintext space. So you should think of it as having a public key which is very long, and in particular, each slot will have a separate subcomponent of the public key. And in order to encrypt, we're going to use a short string, which is going to be the randomness, is going to be shared across all slots. But the fact that we have different public key still allows us to argue security across slots. But then, and in this sense, it's packed because we pack several plaintexts in just a single ciphertext without using too many random coins. And intuitively, the fact that we have a decryption, that we use small randomness, is going to be what will allow us to compute a small decryption hint. So the decryption hint will be some version of the randomness of the dual regger. And again, since it's small and we reuse it across different slots, it's going to be sublinear in the size of the entire plaintext space. And again, it's not exactly CRT, right? But in a sense, you will have to, here you'll have to work over a vector space, right? Instead of just working over just ZQ, you will have to work over, I don't know, ZQ to the power of n, where n is the number of slots. This is not really anything which is conceptually major, but like if you're everything still works. It's just like if you're familiar with this thing, maybe it will be less confusing.
Yeah. Okay, yeah, that's fine. Yeah, I think if there are no other questions, we may end the session here. Any other last question? Anyone?
I have one more question.
Yeah, go ahead, Ron.
So overall, what's the overhead for your construction in computation compared to the FHE by itself?
Oh, good. Okay, so let me say this without overselling things. So for the split FHE, there is virtually no overhead, in the sense that any large computation is just an FHE computation. So you will have some overhead at the decryption time. You will have this, key switching and then hint computing and so on. So, but as far as FHE evaluation is concerned, we are just taking any FHE encryption scheme and evaluating and running the evaluation circuit over it. Okay, so that's essentially it's as good. The answer here is as good as the best FHE encryption scheme that satisfies almost linear decryption. So this might suggest that we kind of have some practical notion of obfuscation, which is far from being true. So we have something which is some practical version of split FHE, but then to get obfuscation, you will have to go through a lot of generic steps, which will degrade the efficiency of your scheme significantly. I mean, everything is still polynomial time, but not with the constants that you would like. So
like the exponential Io to normal.
Precisely. Yeah, precisely. Yeah,
But in addition to this, you also lose something because of this smudging, right? Because you don't have this.
Right. No, you're right. So you have to be a little careful on the you have to be a little careful on how you select the modulo to noise ratio. Yeah, you'll need to have exponential modulo to noise ratio. That's correct.
Yep.
But I guess our focus was really not to get not to get a practical candidate. So we didn't really try to optimize too much in the actual parameters of the scheme.
Yeah.
So in particular, I think it would be conceivable that the same construction could be secure. Maybe not exactly the same construction, but like a similar construction could be made to work even with polynomial modulus to noise ratio. But then, of course, you will have to use some sort of privacy amplification mechanism, because there won't be enough room to get statistical smudging. But this can be done.
So you have such a construction? Or?
So not us, but for example, so we since we could work with smudging, we thought it would just be simpler to just do smudging. But for example, the JLS, so the Jane, Lin, and Sahai, they are really in a settings where they cannot afford to do full-fledged smudging, because they will have to compute discrete logarithm at the end of the decryption. So therefore they want to their smudging operation will have to happen over a polynomial domain, and that's not smudging, right? So like there is some leakage. So they'll have to use some techniques that allows them to boost the privacy of their scheme. So this, I hope this was clear, and I mean,
yes.
There are a lot of details that I omitted, but
I see. Okay. So you think that their techniques for boosting the privacy can be applied in your setting as well?
Yeah, I mean, like I'm not sure why you would apply that, but I think they have, there are even generic theorems that say that, well, I think the theorems are for FE, but I conjecture that something similar could work for XIO as well, that tells you that given a functional encryption scheme that is, well, it's not full-fledged secure, but it's like, let's say 1/epsilon secure, you can boost the privacy of it to 1 minus negligible security. So there are generic statements of this, and I think they are even unconditional. So
Okay. Thank you.
Thanks for the questions.
Thank you very much, Giulio, again, for the very interesting talk. I think we might conclude our session here, and thank you everyone for tuning in, and hope to see you all in our next seminar. Thank you again, Giulio. Thanks, everyone.
Thanks for showing up, and thanks for the invitation. Have a great day.
Yeah, thank you for the nice talk. See you.